Okay, let's go ahead and talk about the linear connections. Okay, so what is a linear connection? Well, a linear connection is a way to identify the tangent spaces at different points on the manifold. Okay, and this enables us to take derivatives of vector fields along curves. Remember in lecture 1, we implicitly used the Euclidean affine connection to take the derivative of a vector field along a curve, because we need to look at the parameterization of this curve, and then basically the tangent spaces along each point of the curve. We want to identify them as the same tangent space, and then the vector field along the curve becomes a time evolving vector in this unified tangent space, and that just gives us a curve in Rn, which we can then take the derivative of to get the derivative of the vector field, a new vector field, right? So it turns out that in general, it's not an obvious process of identifying these tangent spaces, and there is no canonical way to do it with just the Riemannian structure. Now, there is a special thing called the Riemannian connection, which is something I'll talk about later in this video, but let's just say a priori right now, there is no inherent or canonical way to identify the tangent spaces of the Riemannian manifold. And so depending on how we identify these tangent spaces, we're going to get different notions of the derivative of a vector field along a curve, which is what we're going to call the covariant derivative. Okay. So if we look at the example of Rn, all right. First of all, how do we identify the tangent spaces? Well, there's this notion of parallel lines in Rn. So if I take 2 points of an Rn, and I consider lines through those 2 points, I can view those lines as belonging to the tangent spaces of Rn at each of the 2 points. And then essentially, if I want to identify those tangent spaces, I'm basically going to line them up along the parallel coordinate axes. So if I take a vertical axis at one point, I take a different point, I take the vertical axis at that point, I want those 2 lines to be parallel. And requiring that, basically, setting those 2 lines to be quote unquote parallel, meaning that those 2 lines are identified as the same line when we identify the tangent spaces together. That allows us to connect the different tangent spaces of Rn just via simple translation. Okay, and so this process is equivalent to defining the notion of parallel lines, and hence the terminology parallel transport. When we transport the tangent space at one point of the manifold to a tangent space at the other point of the manifold, we're essentially declaring which vectors we're identifying with which vectors, i.e. which vectors are parallel to which other vectors. Okay. All right. So in general, there's no canonical way to do this, but in Rn, there's certain algebraic properties that are satisfied by the directional derivative, or the derivative of a vector field along a curve. Okay. And in particular, the properties that are satisfied are that if I suppose that I have a vector field along a curve, this vector field would be called y, and let's call the curve gamma of t. And let's suppose that I have, a point p, which is gamma of 0. So the starting point of the curve is the point p, and then gamma prime at 0 is going to be my vector x. Okay, so that's basically the tangent direction to the curve gamma at the point p. All right, and so in Rn, if I want to take the derivative of y, of the vector field y along the curve gamma in the direction x, then essentially I just take the directional derivatives of the components of y, the component functions of y. I take the directional derivatives of those component functions, holding the basis vectors fixed, and then that's exactly the derivative of the vector field y in the direction x. Okay, so we didn't even need a curve because, well, we just needed a vector, right? We just needed a vector. We had a vector field y. We needed a point P and a vector x at the tangent space to P. And then we can just take the directional derivative of the vector field y in that direction x at the point P simply by fixing the canonical Euclidean frame, expressing y in terms of its coordinate functions with respect to the canonical Euclidean frame, which is of course constant throughout Rn. And then to take the directional derivative in the direction x, we just simply take the directional derivative of the component functions of y, and that will be the components of the directional derivative of the vector field y in the direction x. Okay, so if you look at this structure, then you look at the structure of the result that you get taking the directional derivative of y in the direction x, you'll notice that it's linear with respect to x. So in particular, right, if we just did this, if we did this process, if instead of x being defined only at the point P, if we let x be a full-blown vector field on Rn, then we could take the directional derivative of the vector. We could take basically the directional derivative of the vector field y in the direction x, which just means take the derivative, the directional derivative in the direction x at every point of the vector field y, and you get a new vector field. Okay, and if you look at this operator, it's essentially an operator which takes in two vector fields and spits out a third vector field. Okay, so it's an operator which takes in a vector field x, which is essentially the direction of the directional derivative, and then it also takes in a vector field y, which is the vector field which we are differentiating with respect to x. Okay, and if we look at this definition in Rn, we can see that there are two important algebraic properties that are satisfied. So with respect to the vector field x, since this is just a pointwise derivation, it really only depends on the value of the vector field x at the specific point P, right? Based on how we've defined everything, then we can scale the vector field x by a function, by a smooth function, okay? And this will essentially scale the vector x at the point P by a constant value at every point. Of course, this scaling factor is going to be smoothly varying because we're basically multiplying the vector field x by a smooth function. Okay, but point is that this will just result in a linear change in the output, which is dxy. We're going to call it dxy. This is the vector field, which is the derivative of y in the direction x. This output vector field will just be scaled by the same smooth function. Okay, and that's just because taking the directional derivative of the component functions at every point, well, that's a linear process. And with respect, of course, with respect to the vector field x. So if we view this directional derivative, or we view this um, operator from two, which takes in two vector fields and outputs a third vector field, then in the first argument, which is the direction of the derivative, in that argument, it's actually c infinity m linear. So it's linear with respect to multiplication by a smooth function. Okay, now what about the second argument? Well, based on how we've defined things, right, these component functions, if we scale the vector field y, which we're differentiating, if we scale that vector field by a smooth function, then the component, by linearity of, we're expressing y in terms of this canonical Euclidean basis, then all of the components will get scaled by that same function. And then when we take the directional derivative, all of a sudden we're going to have a product rule occurring for the components, right? So we take the directional derivative of the component function, let's say fy, or f is our smooth function, and let's say y superscript j. Let's say y superscript j is the jth component of the vector field y. So we take this directional derivative in the direction x, then we're going to have a product rule occurring. Namely, we're going to get the directional derivative of the function f in the direction x times the component function y, plus the function f times the directional derivative of the component function of y in the direction x. Okay, so we're going to have to apply a product rule to the components. So then when we zoom out globally, we see that so when I say zoom out globally, I mean when we add all the components together. That was probably bad use of terminology. So when we look at the overall resulting directional derivative of the vector field fy in the direction x, what we're going to get is essentially f times the directional derivative of y in the direction x plus we're going to get just xf. So the function xf, which is new c infinity function, which is just the pointwise directional derivative of the function f in the direction x at every point. So that's another c infinity function. We're going to get xf times the vector field y. Okay, so this is what's called the Leibniz rule for the covariant derivative. We take d of x comma fy. That's going to be f d of x comma y plus xf y, right? Um, so right. So this is, and then of course in the first argument, what we just explained earlier was that d of fx comma y is equal to f d of xy. Okay, so it's c infinity m linear in the first argument, which is the direction vector field. And so it's tensorial. You could say it's tensorial in the first argument because, again, tensors care only about the pointwise. Tensors require this c infinity m linearity because it essentially represents the fact that it's a pointwise operation. So it only cares about the directional derivative. If we specify the direction x, it only actually cares about the value of the vector field pointwise, which means that it's tensorial in that component. Okay. But in the second component, we have a Leibniz rule. Okay, so we have a Leibniz rule in the second component of this map. Okay, and if we wanted to kind of there's another way to characterize this, which is essentially using the language of tensors and general vector bundles. Okay, and yeah, you can view. I'll just say it briefly, but you can check out Professor Zuoqin Wang's lecture notes. This is from lecture 5 of Professor Zuoqin Wang's lecture notes of the spring 2024 course on differential geometry. At yeah, so and I'm not sure if I'm pronouncing his name correctly. It's Professor Zuoqin, and then Wang, Wang. So all of these lectures that I'm posting are basically my personal reflections off of reading his notes, which are excellent. Some of the best notes I've read in differential geometry. So, anyways, so yeah, you can view this affine connection or this linear connection or what's basically a covariant derivative, right? All of these kind of are the same structure. We can view it as a map which takes in a vector field y and outputs a smooth section of the tensor product of the cotangent bundle with the tangent bundle. Okay, so namely the output, let's say dy of a vector field y, is going to be a 1-1 tensor. Notice it's a 1-1 tensor. This really emphasizes the tensorial nation of the x, the direction vector field. So it's a 1-1 tensor, which basically takes in, if we take a covector field, let's say omega, and a vector field x, right, then the output of this 1-1 tensor is just omega of dxy. So dxy is a vector field, and then of course omega is a covector field, and so this output, the output of this 1-1 tensor is a real number given by omega of dxy. Now, the point is that this is really highlighting the fact that that the argument of the first argument of the covariant derivative is tensorial. It's C infinity m linear. And so if we define the affine connection this way, it's actually can be generalized. This sort of definition can be generalized to just vector bundles writ large, where essentially we require and also, okay, it's not just any map from the um, from C infinity vector fields to C infinity 1-1 tensor fields. It's still going to have to obey the Leibniz rule, which essentially is the requirement that that d of fy, so if you scale the input by the smooth function f, then d of fy is going to be the one form df tensored with y. So the one form df tensored with y plus plus uh, f times dy, right? So yeah, so it's still going to satisfy an analog of the Leibniz rule if you re-express it in terms of this just a map, a linear map from from vector fields, smooth vector fields to 1-1 tensor fields. It's still going to have to satisfy an analog of the Leibniz rule, which I will repeat is basically dy is equal to df tensor y plus f dy. Okay. All right. So let's keep moving on. Right. So what? So once we build this affine connection, okay. Well, all we've done is just added this new structure and called it a covariant derivative. It's not really clear, like why this is the perfect structure, the exact structure that we need. And so that's going to really boil down to the notion of parallel transport. Okay. So this covariant derivative gives us a way of differentiating vector fields along curves. Okay. And that allows us to do something called parallel transport. Okay. And parallel transport along a curve gamma is defined of a vector field. Let's say a vector field y along a curve gamma. The parallel transport of, or sorry, not a vector field y along gamma. Let's suppose we have a vector, let's say x, or maybe I've been using, no, I'll just use x. So let's say we have a vector x defined at the tangent space of gamma of 0. Okay, so we just have a vector at a specific point on the curve. And actually, we want this vector to belong to the interior of the curve. Or actually, does it matter? I don't think that it. No, it doesn't matter. It can be at the edge of the curve as well. But yeah, so let's suppose we have a vector at some point along the curve gamma. Then, if we require, we want to basically find a vector field along gamma such that the covariant derivative of this vector field along gamma in the direction gamma prime of t is identically equal to 0, and we want that vector field to agree with our chosen vector x at the point gamma of 0, point p. Okay, so essentially, given a single vector at a point on the curve, we want to be able to construct a full-blown vector field along the curve such that this vector field, such that the covariant derivative of this vector field in the direction gamma prime of t is identically 0 for all t in the parameterization. And it turns out that the structure that we've given on this covariant derivative, right, it's the right algebraic structure to be considered like a directional derivative, but it's actually enough structure to guarantee the existence and uniqueness of the parallel transport, okay? So if you use, so the proof is the following idea, okay? So basically, we're going to first consider a local neighborhood of the curve, okay, so a small neighborhood. And if we can prove like existence and uniqueness in some small neighborhood of the point of this vector, let's say x, we take x, let's say at a point t gamma of t naught, where t naught belongs to the interval ab of the parameterization of the curve gamma. So we take this vector x, which belongs to the tangent space of M at gamma of t naught, and we construct a small neighborhood of gamma, or technically of the point gamma of t naught, but we construct this small neighborhood in the manifold, and this is also a small neighborhood of the point t naught in the parameterization, right? And the important fact here is that if we can prove existence and uniqueness of this parallel transported vector field in such a small neighborhood, and we can do this for every point, then we can use a compactness argument because the curve gamma we're assuming is parameterized over a compact interval AB, and so we can use a compactness argument to get the global existence and uniqueness because the geometric curve gamma is going to be compact in the manifold. So that being said, let's discuss how to do this. So essentially, we just need to use coordinates. Okay, so if we choose we choose coordinates, and then we're gonna set. We choose a coordinate patch around gamma of t naught, and in that coordinate patch we have a frame. We have a vector frame for the tangent bundle. Okay, and that vector frame, is given by these partial i's, which are varying. Now, instead of the Euclidean case where the vector frame is constant, we now have a potentially varying coordinate vector frame. Okay, and so we basically consider the equation d of gamma prime of t comma x, comma x is identically 0. Okay, and we write x in terms of this coordinate vector frame, so like x superscript I partial subscript I, and then we invoke the Leibniz rule. Okay, and invoking the Leibniz rule, we're going to get the directional derivative of the component functions x superscript I in the direction gamma prime of t. Okay, so the directional derivatives of those component functions times partial subscript I, so times the vector, the component vector of our frame, and then plus the component functions x superscript I times the directional derivative in direction gamma prime of t of the basis vectors partial subscript I. Okay, and then summing that expression over I. I guess we should use a different index. Doesn't really matter. So the point is that if we now want to solve for these component functions, right? We want to show that we can find component functions which satisfy this equation. By the way, that entire expression, so the entire expression I just said, so it's going to be d of gamma prime of t, comma x superscript I, partial subscript I, partial subscript I is outside of the d. So like we have like D parentheses parentheses gamma prime of t, comma, x superscript I, n parentheses, partial subscript I, plus x superscript, let's say k, d of gamma prime of t, comma, partial subscript of k, n parentheses. That entire expression needs to be identically equal to 0 for the definition of parallel transport, okay? And so, and then the important thing is that this coordinate vector frame partial I, it's fixed. I mean, it just depends on the coordinates. Once you specify the coordinate system, then that that coordinate vector frame is something that, you know, is fully determined by those coordinates. Okay. And when I say fixed, I don't mean it's constant. I mean it's just fully specified by the coordinates. And so we're going to get a finite set of functions, which are essentially these d of gamma prime of t, comma, partial subscript k. So the directional derivative of these component vectors in the direction of gamma prime of t, those are going to form a set of smooth functions. Okay. And so what we're going to end up with is a system of differential equations for every component. Okay. For every component, we're going to end up with a differential equation. And so we have a system of basically n differential equations for the components. They're first order, they're homogeneous, and they're linear with respect to these component functions. Okay. And so we can use Picard-Lindelof there. We can use Picard-Lindelof to guarantee existence and uniqueness. Okay, so then these algebraic specifications for the directional derivative are precisely what we need to guarantee existence and uniqueness for parallel transport operation, which is ultimately the geometric goal, or one of the key geometric goals of putting an affine connection onto your manifold, onto your Riemannian manifold. Okay, so that's good enough for now.